All right, so we are going to do some linear application problems, but before we get to that, we're going to work on something called unit analysis. And this may or may not be something you've seen. They do teach it in the science classes. They teach it in chemistry. I know they do it in physics, but if you haven't had chemistry or physics, you might not have seen this before. So basically, for unit analysis, it's a way to figure out the units, and it's also a way so that the units can help you figure out the problem. So it's pretty cool, really, when it works well. So for unit analysis, the units cancel like numbers. All right, so we're going to do some examples. First one we need to do is establish what does the actual physical problem look like. So we've got feet divided by seconds. Now this is one where we're not going to be canceling anything, but you do need to know how to interpret that. Remember that your division symbol is a little fraction and that the first one goes on top, the second one goes on the bottom. So when you create this as part of your answer, you're going to have feet over seconds because the first one goes on top, the second one goes on the bottom. When you have a unit with a fraction bar, the fraction bar is interpreted as per. So this would be interpreted as feet per second or feet per 1 second. You can put a 1 in there. But again, the per comes from the fraction bar. All right, let's do another example. Let's say you've got kilometers per hour times and hours per minute. And you're trying to simplify the units down to where you have one answer instead of all these pieces and parts. So again, the per means fraction bar. So you're going to put kilometers over hours. The word per tells you the bar goes there. Times. And then we've got hours over minutes. And then this is where it's a lot like prime factoring. You go tops times tops. So kilometers times hours over bottoms times bottoms, hours times minutes. And just like in prime factoring, when you cancel out the same factor, this is the same way. Hours go into hours one time, and your simplified units are kilometers per minute. All right, last one of these I'm going to show you. Let's say you've got centimeters divided by centimeters per foot. Okay, so in this case, centimeters goes on the top, so centimeters over 1, all over, and then you have a fraction on the bottom because of the word per, you've got centimeters over 1 foot. So just like when we did stacked fractions, to get rid of the bottom fraction, you multiply by the reciprocal. So times feet over centimeters, which means you multiply the top times feet over centimeters. And just like stacked fractions, the bottom completely cancels to 1 because feet goes into feet 1 time, centimeters go to centimeters 1 time. So the entire bottom is now 1, so it can be disregarded. And on the top, we have centimeters times feet over centimeters. The centimeters divide out, and our units end up being feet. So yes, we're using a little bit of everything we've learned. All right, and these things are going to come up in a problem when you're trying to figure out the units of the answer. All right, so Roman numeral 2, U.S. postal regulations, bless you. U.S. postal regulations. I have to find it. Okay, so basically for U.S. postal regulations, there's a package that has the length plus the girth equals 108 inches. And then it goes on a standard shipping rate. So, for example, we have a package that is 48 inches long, and the total sum of the dimensions equals 108. So what they want you to do is figure out what are the other two dimensions. We know how long it is, we know the sum, but we want to know the other two dimensions. So what we're looking for the other two dimensions are the height and the width. Okay, so this is a little artistic here for some of you. I want you to draw a rectangular box. You do that by drawing a rectangle. And then you draw the same length of line, parallel and 3 times over, and then connect the backs. That's how you draw a box. So in order to do this problem, you've got to know what the post office means by girth. So your girth of your package is bottom, side, top, side. That is your girth. And then the length is the longest measurement on it. That's the length. So we have the length. The length is 48 inches long. So we got that part, but we got to figure out what the girth is by writing an equation. Now, the one assumption you have to make on this, otherwise it's not possible to solve it, is that the girth would have to be the same length because we can only solve with one variable. So if x is the length and x is the height, the girth is x plus x plus x plus x. So we have a 48-inch length plus the girth, which is x plus x plus x plus x. And they've told us that the sum of all those dimensions are 108 inches. And that would be your equation to try to figure out the missing height and weight. So I'm not going to do this whole problem, but x plus x plus x plus x is 4x plus 48 equals 108. I'm just going to put dot, 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 and x ends up being 15 inches. And that would be your height and your width. So on your homework, you're going to have a girth problem. You're going to have a U.S. Postal Service problem. So you can use this one to help you figure it out. Okay. Roman numeral 3. A graph intersection problem. Graph intersection problem. Okay. So if you're given a graph and you're supposed to read it, we want to talk about how you can interpret a graph. So over here on the side, we're going to make an L-shaped graph. And one of the lines starts out higher, but it's kind of flat looking. The other line starts out at 0, but it's steeper looking. And your graph is time in days for the bottom part. And the side is quantity in dollars. And how do we actually interpret a graph like this? Assuming we have two different rates that we're looking at. Okay, so I'm just going to make the red line rate 1 and the blue line rate 2. How do we actually go about interpreting this? Okay, so where the rates intersect each other, which is right here, corresponds to a certain amount of money. So the intersection on the graph is the break-even point. And we've talked about the great break-even point before. It's where the two rates are actually the same. Now, the left side of the graph, unless they tell you otherwise, starts at 0, and the y-axis starts at $0. So looking at this, it looks like rate 1, you start out paying 0 money, but then the rate is steeper, so you're going to pay a higher rate. So red line starts at $0, but then it's a higher rate. And you can tell it's a higher rate because the line is steeper than the other one. Now, the blue line starts at some quantity. So the blue line starts at, we don't know, some number of dollars because it starts up here. So you're obviously paying a certain amount of money to for the get-go, but the line is flatter looking. So plus the rate is a lower rate. It looks flatter. So even if you have no idea what this problem is about or what the rates are, you can interpret what that graph tells you. The graph tells you that rate 2 is cheaper until the break-even point. So rate 2 is cheaper until the break-even point. I'm sorry, I messed it up. Rate 1, not rate 2. Sorry. Rate 1 is cheaper until the break-even point. Then, after the break-even point, rate 2 is cheaper. So after rate 2 is cheaper. So if we can just figure out where the break-even point is, then we can figure out which rate will be cheaper for us depending on how many days of whatever this is. So the break-even point shows you where one rate is higher than the other and where they change places.
I thought it was like hotel rates, maybe.
This one didn't have his topic. Could be hotel. All right, Roman number 4. This is a diagram approach. Some questions you really just need to make a good diagram. And these are questions that involve measurements, or if they're giving you dimensions of something like width and length and the width of a frame, a picture frame, or of a concrete walkway, just whatever they're giving you is like obviously the dimensions of something. So here's an example of this kind of a question. 3 pictures that are 2 5/8 inches wide are placed on a page that is 11.5 inches wide. If you leave equal space between the pictures, how much space can you put between the pictures if the left margin is 1/4 inch and the right margin is 1 5/8 inches? So this is one where we've got measurements all over the place, and then we've got pictures sitting on a page. So this would be an ideal question to draw a diagram and then label it. So what we know is we have a page. So I want you to draw a nice wide rectangle. So we need space to label. And we know we're putting 3 pictures on it. Okay, so 1, 2, this is really, I didn't do a good job drawing to scale, but there you go. 3 pictures. Here, I'll fix it. Let's see. There, that's a little better. All right, and here's where you just label the heck out of everything. The pictures are 2 5/8 inches wide. So 2 5/8 from edge to edge, 2 5/8 from edge to edge, 2 5/8 from edge to edge. Okay, so label that. They're going to be placed on a page that's 11.5 inches wide. So from here all the way over there, is 11.5 inches. That's going to be an important number because we can't shrink the page or make the page larger. It's 11.5 inches. Now, here's where it says, if you leave equal space between the pictures, how much space can you put between them if? So what we're trying to find is how much space we can put between the pictures. So let's call that distance x, and that will be the same distance between the pictures. And then it says the left margin is 3/4 inches. So this is 3/4 inches from the picture to the left. And the right margin is 1 5/8 inches. And our goal is to find x, which is the number of inches between the pictures. Okay, so you have a total width here and a bunch of things that don't overlap. So all of these things need to add up to 11.5 because that's as big as it gets. So let's start with the 11.5. 11.5 equals, and 3/4 plus, now 2 5/8 is 16 21/8 plus 21/8 plus x plus 21/8 for the middle picture plus x again plus 21/8 for the right picture plus, let's see, 8, 9, 10, 11, 12, 13, 13/8 for the right-hand margin. So all I did was convert them to improper because we need that. Oh, I should have converted the 11.5. That would be 23/2. All right, that is your equation. And most likely for this equation, you'd want to clear the fractions because that's a heck of a lot of fractions. So, you can make them all 8. So if you multiply this one by 2/2, multiply the x by 8/8, multiply the other x by 8/8, and then multiply 23/2 by 4/4. So if you make all the bottoms 8, then you can cancel out the bottoms. And you have 23 times 4, which is 92, equals 6 plus 21 plus 8x plus 21 plus 8x plus 21 plus 13, which is a whole heck of a lot easier to solve. So basically we added up all the measurements equal to the page width, do them improper, clear the fractions. And again, I'm not going to finish. You know how to do this. X equals 5/8 inches ends up being the answer. So some questions you're going to want to do a diagram. Yes. Not in the notes. Okay, last section. Algebraic approach. Some questions you can just use a straight up algebraic approach and it's going to work just fine. So here's an example of a question. But first, how do you attack a big picture question? Okay, so number 1, you want to write the big picture. What's the big equation you're going to go for in words? And you're going to look for totals or equal amounts because that will tell you how to put it together. If they give you a total, you'll have a bunch of stuff added together equals the total, and boom, you've got your equation. If they tell you 2 amounts are equal, then you're going to set it up amount 1 equals amount 2. So those are the 2 things you're going to look for in the problem. Once you've got that, so you know the basic overview of it, you're going to designate X. What is it that you're trying to figure out? And then solve. Okay, so here's an example. At North High School, 176 students buy non-spiral notebooks from the school store. This number has been increasing at a rate of about 24 per year. The number of students buying spiral notebooks is 331 and has been decreasing, but at a rate of about 15 per year. At these rates, when will the number of spiral notebooks sold be half the number of non-spiral notebooks sold? So the big picture is we want to know when the spirals will be half the number of the non-spirals. So that is your big picture equation, that the number of spirals are going to be 1/2 the number of non-spirals. So that's step one. We looked for the big picture. We figured out what was going to be equal. All right, what are we trying to do? What are we trying to find? Number of years. When is that going to be equal? So X is the number of years until this happens. All right, so now that we figured out what X is, we're going to start using the calculations. So let's start with the non-spirals. 176 students bought non-spirals, and it's been increasing, so plus, it's been going up at a rate of 24 per year. So times X number of years, 24 per year. The spiral notebooks, this year, 331 students bought it, but those numbers have been decreasing, so we subtract at about 15 per year, so 15 times X. So now that you have an expression for non-spirals versus spirals, put it into your big picture. So here we go. Spirals, 331 minus 15X equals 1/2, and then our non-spiral is 176 plus 24X. And you have your equation. And again, just put ... X ends up being in 9 years. One will be half the other. So write the big picture, figure out what X is, and then try to write expressions for parts of your big picture. Right, that is the end. Now, question.